That's all. I take it. It's all looks good. The first announcement. So don't forget that we have a YouTube channel. You'll all have access to it. But if you after the meeting, when you don't see the channel, you can always go and find these all the videos on the just by searching for quantum battles. On Twitter, we try also to put everything on Twitter, and obviously all the posters and wonderful videos related to the posters and also to the session can be searched on Twitter. So please check. All you need to do is just to put the hashtag Attoscience, and you will find all the materials, wonderful materials related to the conference. One more important thing, that's a special issue in APGD is planned, and the deadline is the 31st of December. So be prepared. Please think about this, and with the deadline is 2020. And before we actually start enjoying our session, I'd also like to stop sharing my screen. And I'd like to remind you that for the Q&A session, you can either ask your questions in the chat. You can also put your questions in the Slack. We would also like to get a more feeling of the audience. So you can also raise your hand, and then our Zoom master will let you speak. And we'll see your face, so they have a chance to see your face. And now I'd like to ask you to test this option. So can everyone to try to raise their hands? If you, yes, yeah, that's working wonderfully well. Exciting, very well. I'm not gonna give you access to the microphone now, but please try to raise your hands, and we see you're all active. Brilliant. Thank you very much. Okay, and with this, I'd like to give the floor to our first speaker, Mark Tracking, who will be talking on Attosecond entanglement and coherence. Please, Mark, that's your floor now.
Okay, thank you very much. At the start, I first of all also would really like to thank Carla and her team for putting together this event. I think it's really exciting that in these difficult times that we nevertheless through this format are able to have such an exciting time together. So thanks a lot, Carla, for this. It's really fantastic. So my talk this morning, in a way, is a very natural continuation of what Robin Santra was talking about yesterday afternoon. So Robin talked to us about several ways that the degree of coherence is determined in Attosecond experiments. And what I would like to talk about in my talk this morning is particularly the role of entanglement in determining the coherence that we encounter in Attosecond experiments. So here's a summary of my talk. The main point that I want to discuss with you, or what I'm going to try to convince you of, is that in Attosecond science, we encounter, in a way, complementary roles of entanglement and coherence. Now, of course, in order to understand this statement, we first have to be a little bit more precise about what we mean with entanglement and what we mean with coherence. So let's start with coherence. And there, of course, we have to realize, I hope we all do already, that any time-resolved experiment, any pump-probe experiment that we do in our laboratories, of course, relies on the fact that there are well-defined phase relationships between different component states that together form a coherent superposition, that together form a wave packet that we are probing in our experiment. Of course, in Attosecond science, we encounter this everywhere. We encounter this the moment that we are talking about electronic wave packets that are involved in charge migration processes. We encounter this in nuclear wave packets when we consider the dissociation of a vibration of a molecule. Really, the key element that makes our pump probe experiment possible always is the existence of coherence in the experiment. Now, in Attosecond experiments, coherence is potentially compromised, and this has to do with the fact that Attosecond radiation, so the Attosecond pulses that we generate by means of harmonic generation, are by definition ionizing radiation. Attosecond pulses that we generate have photon energies in the extreme ultraviolet or even in the soft X-ray regime. And for any atom, molecule, even for condensed phase systems that we use, this represents ionizing radiation. This is radiation that can split the system into an ion and a photoelectron. And what I'm going to try to convince you of is that more often than not, there is going to be an entanglement between these ions and these photoelectrons. And this entanglement limits the coherence that we can observe when in our Attosecond experiment, when we choose at dynamics that is taking place in the ion, or when we choose to look at dynamics that is taking place in the photoelectron. And I'm going to try to illustrate this point in two ways. One is I'm briefly going to talk about an experiment that we already did quite a few years ago, where we first encountered this. And then I'm going to tell you about a numerical experiment that I performed recently that also illustrates this point. So let's start with the experiment. This was at the time actually the first Attosecond pump probe experiment on a molecular system that we performed in the laboratory of Mauro Nisoli in Milano. And it was a classic XUV-IR pump-probe experiment where we used an Attosecond pulse to ionize the hydrogen molecule. That basically then led to production of H2+ in the two lowest electronic states of the molecular ion. So either the bound 1s sigma G state or the repulsive, therefore unbound 2p sigma U state. And at a variable time delay, we came in with a few cycle IR probe laser, and then that resulted in the production of H+ ions that were measured on a velocity map imaging detector. So this velocity map imaging detector basically means that we projected the ions on a 2D detector, and the position where we measure the ions on this detector basically has the meaning of velocity. So that basically means that in the experiment, we had access both to the actual velocity of the ions, their kinetic energy, as well as their direction of emission with respect to the laser polarization axis, which actually is the vertical axis in the image that you see here. Now, the observable that we chose to focus on in this experiment was so-called electron localization. Basically, the difference in the tendency for the H+ ion that is formed in the dissociation of H2+. Of course, we form an H+ and we form a neutral H atom. Basically, the tendency of the H+ that is formed here to preferentially fly up or down along the laser polarization axis. So that is expressed in the asymmetry parameter that you see plotted here, which is basically the normalized difference between the probabilities for the H+ to fly up or down along the laser polarization axis. Now, there's several things that you see in this experimental result. First of all, you see that this asymmetry parameter isn't necessarily zero, so there is a preferential direction up or down. And moreover, we see that this preferential direction depends on the energy, the kinetic energy of the H+, and most interestingly, it depends on the time delay between the Attosecond pulse and the few cycle IR pulse. And in fact, we see the asymmetry oscillating back and forth as a function of time delay. So if we shift the time delay by half an optical period, we shift the preference from up to down or the other way around. Now, first question is, why is this an experiment that tells us something about coherence in the H2+ ion? In order to appreciate this, what I'm trying to convince you of is that electron localization is in fact a manifestation of coherence. Why is that so? Well, the reason that this is so is that there's a way that we can write the electronic wave functions that belong to the 1s sigma G and the 2p sigma U states. And basically both of them we can write as linear combination of atomic wave functions. The precise nature of these atomic wave functions is not important for now. But we can write them as a linear combination of atomic wave functions where the single bound electron that we have in the H2+ is located on the left or on the right proton that we have in the H2+. And then the difference between the 1s sigma g and the 2p sigma u is simply whether we have this linear combination with a plus or a minus sign. The plus sign, of course, indicates that there's a finite electron density between the two protons. That's why it's a bonding orbital. The minus sign indicates that there's a node between the two protons. That is why this is a repulsive state. Now, of course, we can easily rewrite this, and then we can see what it means for us to find the electron on the left or the right in our H2 plus ion. And of course, the moment that we see an electron on the left, that means that we are going to detect an H plus on the right and vice versa. And so we basically see that in order to have the electron preferentially on the left or on the right in our H2 plus, we somehow must have put the molecule into coherent superposition of the gerade and the ungerade state. We must have broken the parity of the ionic wave function so that the ionic wave function is a coherent superposition of gerade and ungerade. So that is why this electron localization really measures for us the electronic coherence that we have in the ion. Okay, that's all fine and good, but why is this then an experiment that is sensitive to entanglement? Now, in order to appreciate that, I am writing down this form as a general way to describe the ion plus photoelectron wave function that we have in the H2++ electron system. So basically, you see that there's two choices that we can make here. It's a little bit of simplified notation, of course. And so the first choice that we need to make is that we're going to produce an ion that is in the 1s sigma g, so in the gerade state, or that is in the 2p sigma u, the ungerade state. And then in addition, what I'm distinguishing here is that there is an accompanying photoelectron. And also this photoelectron has a parity. If the angular momentum of the photoelectron is even, then the parity is gerade. If the angular momentum of the electron is odd, then it's going to be ungerade. And so that basically means that I have four combinations of ionic states and photoelectron states, depending on whether the parities are gerade and ungerade. Of course, if the parity of both the ion and the electron are gerade, then the overall wave function is gerade, and so forth. So this general form of the wave function in simplified notation already tells us that it's rather likely that we are going to encounter entanglement. Because after all, what does entanglement mean? Entanglement means that we are unable to write the wave function of our two-component system as a single product of a wave function for the one part and a wave function for the other part. What we see here in our H2++ photoelectron system is that we potentially have four of these products that play a role in the experiment. And the moment that we have more than one, we have an entangled system. Okay, now let's return to the electron localization, and let's use the expressions that we had on the previous slide for the wave function corresponding to the electron being left on the left or on the right. Let's introduce these in these expressions. That's of course easy to do. So what I've done here now is simply replace psi g and psi u by the expressions that we had on the previous slides for psi left and psi right. Now, in doing that, we can come up with expressions for the probability that in our experiment, we are going to find the electron on the right or on the left. That's of course very easy to do. We just collect the amplitudes that correspond to left or right and take the absolute value squared. And so that basically leads to these two expressions for the probability to find the electron on the left or on the right. And we basically see that all four of these coefficients play a role in this. The only difference between the two expressions is that on the left side, we have two of these amplitudes combining with a plus sign. On the right side, we have two of these amplitudes combining with a minus sign. Okay, now let's consider what we do when we ionize a neutral H2 molecule with an XUV photon. I mean, this is a process that is subject to a dipole selection rule. And this dipole selection rule basically tells us that the overall parity of the ion plus photoelectron wave function that we produce must be ungerade. So that basically means that not all four terms are accessible to us here. And specifically, it's the C1 term and the C3 term that represent here gerade states that we cannot reach in single photon ionization. Now, what happens if we set C1 and C3 equal to 0? Then we basically see that I left becomes equal to I right. We lose the ability to introduce a difference between left and right, we cannot produce electron localization, laboratory frame electron localization in single photon ionization. And so basically what we see here is that the entanglement of the ion with the photoelectron prevents that in XUV ionization, we form the molecular ion in a coherent superposition of 1s sigma g and 2p sigma u. And that is what's needed for electron localization. So attosecond ionization by itself cannot produce electron localization. So how then does it come about that in the experiment we do in fact see electron localization? Well, of course, the experiment is a pump-probe experiment. It doesn't just consist of the attosecond ionization. There is also an IR probe laser. And what I will try to show to you now is that it is in fact this probe laser that converts the entanglement that we have in the initial ion plus photoelectron state into coherence in the ion, into a coherent, in the possibility to observe a coherent superposition of the gerade and the ungerade ionic state. Now, how can the IR do this? The IR can do this in two ways. One thing that the IR can do is that it can interact with the molecular ion. It can pump the molecule from the ground state to the excited state, or conversely, by stimulated emission, we can come down from the 2p sigma u state to the 1s sigma g. And so basically, the IR can interconvert the 1s sigma g and the 2p sigma u, and that is a way to get non-zero amplitudes for the C1 and C3. And the moment that we do that, as we saw on the previous slide, we have the ability to see an electron localization. Interestingly, there is a second way that the IR laser can do this, in the sense that the IR laser can also interact with the outgoing photoelectron. That IR lasers do this very efficiently is something that, of course, we know. We use it in streaking experiments, we use it in rabbit type experiments. That basically means that the IR laser can change the angular momentum of the outgoing photoelectron that is entangled with the ion, and that also is a way to create coherence in the molecular ion. And in the analysis of the experiment that we did, like I said, about 10 years ago, we could convince ourselves that in fact both of these mechanisms played a role, although at the time we were a little bit nervous about using the word entanglement in this context. But that's basically the conclusion of this work, is that the IR probe laser converts the very high degree of entanglement that we have in the initial ion plus photoelectron state that prevents us from having coherence in the ion, that therefore prevents us from having electron localization. The IR laser converts this entanglement, and as a result of that, we get a coherence in the ion, we get an observed electron localization. Okay, so this was an example of the way that entanglement is involved in determining the degree of electronic coherence in a molecular ion. What I now would like to turn to is the role that entanglement plays in vibrational coherence. I mean, the moment that we ionize an H2 molecule with an attosecond pulse, as I've said, among the possibilities that we have is producing the bound ground state of the molecular ion. And in this bound ground state, actually, we will populate a superposition, a coherent superposition of vibrational states. And that basically means that we will form a vibrational wave packet. Now, as you see in this experimental result, this vibrational wave packet is very easy to detect, in the sense that we have a situation where if the vibrational wave packet is at the outer turning point, then it's very easy to dissociate the molecular ion by a single photon absorption from the 1s sigma g to the 2p sigma u state. On the other hand, if the vibrational wave packet is at the inner turning point, this takes many photons and is very inefficient. And so simply monitoring the intensity of H pluses as a function of XUV-IR pump-probe delay maps out this vibrational wave packet motion, and we see the dephasing and rephasing that has been seen in many of these types of experiments. Also, we can take a Fourier transform, and then what we recognize is that all the frequencies that we encounter in the experiment are simply the result of quantum beats that we have between adjacent vibrational levels, as we expect for this type of experiment. Now, what I want to do in the next part of my talk is take this one step further and basically show you the results of a numerical experiment where I've done calculations on this vibrational wave packet dynamics, but now with a sequence of 2 attosecond pulses where I induce a variable time delay between these 2 attosecond pulses. This is something that we are beginning to do in the laboratory, and that in general with high harmonic sources, people have already been able to do. And what I'm going to try and show you is that this provides a way to more or less coherently control the degree of entanglement or conversely the degree of ionic vibrational coherence that we get in our system. So what are we going to do? We're going to propagate the two-dimensional Schrödinger equation for the H2 molecule. We're going to assume that the H2 molecule is aligned along the laser polarization axis. And we're going to assume that one electron is going to remain bound, and we're going to make the Born-Oppenheimer approximation, putting this electron either in the configuration for the 1s sigma g or the 2p sigma u state. And then what we do is a 2D calculation with 2 degrees of freedom, 1 degree of freedom for the internuclear coordinate, the vibrational or the dissociative coordinate, and 1 degree of freedom for the second electron, which is free to move along the laser polarization axis. And that is in fact the electron that is going to be ionized by the Attosecond laser pulse. And then what we do in the calculation is determine the joint energy spectrum of the photoelectrons that are produced by the XUV pulse and the fragment ions that are produced by the probe pulse. And I've done this using the time-dependent surface flux method. So on this occasion, I would say a big thank you to Lars Madsen and Dieter Bauer, who a few years ago have written some very nice, beautiful papers about the implementation of this method for hydrogen. And I've benefited greatly from that when doing this work. Okay, so a few numerical details. The results that I'm going to show you are results where I have an Attosecond pulse that is centered around 0.8 atomic units, so about 22 electron volts. And I'm going to probe the vibrational wave packet with a probe laser that has a photon energy of 0.1 atomic unit, so about 3 eV, roughly 400 nanometers. A few details about the electron and the ion grid. Of course, the nice thing about this T-surf method is that it allows propagation over very large times at a very moderate cost, given that beyond a certain electron radius and beyond a certain internuclear distance, the wave functions are projected onto Volkov states and plane waves, and makes the whole propagation very, very efficient. Okay, so here I show you a few results of these calculations. So here I show you 3 results. So 3 pump-probe scans where we look at the H plus kinetic energy distribution, or here it's plotted as momentum distribution, as a function of XUV-IR pump-probe delay. And for the XUV pulse, we actually have a pair of pulses with a delay here of 0 atomic units, 450 atomic units, about 10, 12 femtoseconds, and 900 atomic units, about 20, 22 atomic units. So basically for a delay of 0 atomic units, a single isolated Attosecond pulse, we see a vibrational wave packet motion very similar to what we saw in the experimental result a moment ago. We see the dephasing, rephasing. It basically looks very similar to the experimental result. The same can be said for the result that we get with an XUV delay of 900 atomic units. Looks very, very similar to what we have at 0 delay, but we have a very different situation when we have an XUV delay of 450 atomic units, about 10 femtoseconds. In this case, we don't really see the fundamental vibrational frequency anymore. We do see some high frequency oscillations, but much less pronounced than in the other 2 cases. And what I'm going to try to convince you of right now is that this is a result of photoelectron ion entanglement. So basically entanglement between the electron and the ion that prevents the emergence of a pronounced coherence in the vibrational wave function of the ion. So how will I demonstrate this to you? Well, first off, when you have such a time-dependent trace, of course, it's useful to perform a Fourier transformation to see which frequencies underlie the time-dependent trace. And on my next slide, I'm going to do that for these 3 traces, as well as a lot of additional delays between the XUV pulse. And so basically what and I'm going to do that at the energy that is indicated here by the yellow line, so basically for a proton momentum of about 10 atomic units. Okay, so that leads to this graph here. And so here we see the frequency content of these vibrational wave packets as a function of the 2 pulse delay, as a function of the delay between the 2 isolated Attosecond pulses that I've used to ionize the molecule and to initiate this wave packet motion. The frequencies near 0.007 are the fundamental frequencies, so basically the frequencies corresponding to adjacent vibrational level spacing. To some extent, we also see double the frequencies. Those basically are coherences between vibrational states that are separated by two quanta. When we look at the fundamental frequencies, then we recognize the behavior that we saw in the initial in these initial traces that I showed a moment ago. And so we see pronounced fundamental frequencies for zero delay, also for 900 atomic units delay, and a near absence of these vibrational frequencies when the delay between the two attosecond pulses is about 450 atomic units. And my claim is that the fact that we see these frequencies very pronounced at these delays of 900 or also double 1800 atomic units reflects the fact that here we have a high degree of coherence in the ionic wave function, whereas at the other delays, we have introduced a high degree of photoelectron ion entanglement that prevents this vibrational coherence. Now, and in order to prove to you, or try to prove to you that this is the case, I would like you to look at this diagram here, where where I'm considering the ionization of an atomic or molecular system into two final ionic states. So, for example, two of my vibrational states in the H2 plus system. And I'm considering this for different time delays between the two attosecond pulses that I use to ionize. So the two delays that I'm showing, the delay on the left is where the delay is equal to 2 pi divided by the energy difference between the two states that I'm considering. The delay on the right that I'm considering is basically half of that, is pi divided by the energy difference between the two states that I'm considering. Now, obviously, when I have a delay between two pulses, I induce fringes in my XUV spectrum. In the case on the left side, these fringes basically have an energy spacing that is equal to the spacing between the two levels that I have assumed. In the case on the right, at half the delay, the spacing between these fringes is twice that, is twice the energy difference between my states. And now let's turn our attention to the graphs at the bottom, which basically are photoelectron spectra that we expect to be able to measure the moment that we ionize our system with these pulses, with these XUV spectra, and basically with red and black labeling whether we are ionizing into the E1 or the E2 final state that I have assumed. So first, let's look at the case on the right. I hope you can see my cursor here. And what we see there is that if I measure a photoelectron energy at this energy here that I'm currently indicating, oops, I don't see my, yeah. And so basically at the peak of one of these red oscillations, then you see that at that energy, the probability, to measure a photoelectron in coincidence with the other state, the E1 state, is virtually zero. In other words, the moment that I measure a photoelectron at this energy, it essentially tells me that I have produced state E2. In other words, at that point, there's no uncertainty anymore about whether I've produced E1 or E2, and there is no vibrational coherence. Likewise, if I produce a photoelectron at this energy here, I'm now pointing at one of the peaks in the black curve, then I know with a very high degree of probability that I've produced state E1, and that state E2 has not been formed. In other words, again, there is no vibrational coherence in this case. And so this is basically a case where there's a very high degree of entanglement between the photoelectron and the ion. If I choose to do a measurement on the photoelectron, determine its kinetic energy, then it pretty much tells me what ionic state I have formed. And in that sense, I do not have a vibrational wave packet. Now, the situation is very different on the left. So where the fringes that I have in the XUV spectrum are equal to the energy difference between these two states, there we have a situation where the two photoelectron spectra look very, very similar to each other. I mean, one is just shifted by the energy spacing between the two states with respect to each other. But basically here we have a situation that even if I were to measure the energy of the photoelectron, it really doesn't tell me whether I have formed state E1 and E2. So this is a case where I have a low degree of entanglement, and as a result of that, I have a high degree of vibrational coherence in my system. And so this basically underlies what we saw in this graph here, As a function of time delay, we induce fringes in the XUV spectrum, and these fringes either lead to a high degree of entanglement between the ion and the photoelectron. In this case, I will not see a vibrational wave packet, or they lead to a low degree of entanglement between the ion and the photoelectron. And in this case, I can measure an ionic vibrational wave packet with a high degree of coherence. Okay, so that's the main message of my talk. I briefly at the end want to show you that we are now also beginning to try and do these things in the laboratory. And so in the laboratory, obviously, if we're looking at entanglement between ions and photoelectrons, then we would like to be able to measure these in coincidence. Now, this is basically where my talk then continues the talk of Robert Mooshammer yesterday. I mean, the method of choice there obviously is going to be then the Coltrane's method. And in order to do that, as Robert also explained yesterday, we need high repetition rate in our experiment. Now, in order to do that at MBI, we've developed a 100 kilohertz attosecond experiment. So we've built a 100 kilohertz non-collinear optical parametric amplifier that generates something like 7 femtosecond pulses, few hundred microjoules, so quite comparable to what we commonly get out of a hollow-core fiber compressor when we use a Ti-Sapphire system. We have in fact further compressed these pulses using multiple plate continuum generation, also using a hollow-core fiber compressor, and there we get near single cycle operation. So that's already very good for isolated attosecond pulse generation. Of course, if we want to generate isolated attosecond pulses, then carrier envelope phase control is very important. And we have confirmed the carrier envelope phase stability of our system. So here you see results of an experiment that we've done together with the group of Gerhard Paulus, where we've done a single shot, every shot CEP measurement of the system. And the CEP quality that we have here is really fully compatible with reproducible isolated attosecond pulse production. Recently, we have confirmed the isolated attosecond pulse production. So here you see a streaking trace that we have recorded. This is not yet recorded with the Coltrane's apparatus. In this case, we hooked up a velocity map imaging spectrometer to the setup. Here you see the measured streaking trace. And here you see a retrieval. This is a retrieval using the Volkov transform generalized projection algorithm that was developed by Franz Kärtner and co-workers. The important thing about this algorithm is that it doesn't make the central momentum approximation, and that is very important to us because many of the photoelectrons that we detect in this experiment are relatively low energy, and of course, we also detect them over a very large bandwidth. So these are basically the retrieved pulses. So basically what we see is that we form isolated attosecond pulses with a duration of more or less 140, 150 attoseconds with a very nice pre and post pulse contrast. Pre and post pulses are well below 1%. So this is really a quite high quality source of isolated attosecond pulses. It's also a relatively efficient source. We generate at least something like 10 to the 6 photons per pulse. And that is really compatible with doing Coltrane's measurements. And in fact, at the moment, we are beginning to do these measurements. Okay, so that brings me to the end of my talk. So my summary, attosecond experiments rely on the existence of coherent superpositions. And I've tried to convince you that the coherence that we need there is often limited by entanglements. I've shown you that coherent control techniques may allow us to overcome these limitations by tuning the sequences to coherences of interest. That's something that may be particularly interesting when we try to do charge migration experiments, where we try to build coherent superpositions of specific states with specific energy spacings. And I've also very briefly shown you the progress that we are making with the experimental implementation of some of these ideas. Finally, I want to acknowledge Federico Furch, Michael Zolotkov, Tobias Witting, Klaus-Peter Schulz, who basically together developed the attosecond experiment that I showed you at the end. And I very much want to thank you for your attention.
Thank you very much, Mark. A very interesting presentation, and also for the very exciting results. I'd like now to go to the Q&A session, and we got one question ready from the audience, and we have time for this. So Mark, it's a equation. It's a equation from the Reiner-Dörner. Mark, I fully agree with your description of entanglement, but a persistent person from quantum optics would claim that to experimentally prove that the system is entangled rather than only classically correlated, one needs to do a belt test. Is there a trick how to do a belt test in these experiments, experimentally rather than only theory?
Yeah, that's a very good question, a very interesting question. I can tell you that last year, I've spent a few months trying to come up with a belt test in this context. Unfortunately, I mean, it may be possible, I don't know. I have not found it yet. I have not found a way yet to let's say, map the experimental protocol that one would use in a belt test to map that onto, let's say, the experimental capabilities that we have in an Attosecond laser lab. It may be possible, but I have not found a way yet. But it would, of course, be incredibly exciting if we could do that.
Thank you. There are two more questions. Maybe I allow a couple of minutes to that, even though we're running out of time. The Emilio Pisanti asked that the theory toolbox from quantum information provides several useful measures of entanglement. Have you looked at those measures for the numerical simulations of H2 you presented?
Yes, absolutely, and I totally agree that that's a very interesting way to proceed. I mean, the project that I'm reporting you on today is still ongoing. In fact, it's very much made possible by the Corona pandemic that gave me a little bit of free time to work on this problem that I had wanted to work on for some time already. And in fact, what you're suggesting is exactly what I'm doing at the moment. And what I'm finding is indeed that the observations that I'm making in the simulations that I showed you here today, they are consistent with what you would expect the moment that you apply these quantum optics principles. And so, for example, one of the things that you can do is determine the purity of the wave function for the different conditions, as a function of XUV pump delay. And then, in fact, you see pronounced oscillations in this purity going back and forth between situations where there's a high degree of entanglement and situations where there's a high degree of coherence. So yeah, I very much agree with your question. It's exactly what I'm doing at the moment.
Thank you, Mark. There was a comment, so it's not a question, so you don't need to answer, is that it's enough to measure proper entanglement weakness, which should be easier in general than the belt test, from Marseille Levenstein. And Reiner-Dörner said, I agree, we also failed. So with this, I'd like to thank Mark again for this exciting presentation and like to move to the next presenter. The next talk is on Attosecond photoemission dynamics. It will be given by Pascal Salieres. Pascal?
Yes.
It's now, the floor is yours.
Thank you, Sergey. So I'm trying to share my screen. Okay, here we are. So good morning. The title of my talk today will be Attosecond photoemission dynamics. And since we are in a session about quantum interferences, what I would like to discuss is how we can use quantum interferences to get deeper and deeper insight into photoemission dynamics. First, to get access to ionization delays, then to get access to more complex ionization dynamics, and then how we can access to decoherence in the photoemission. So first, let me go back to basics and recall that quantum interferences have been central to the field of Attosecond science from the very beginning. And this is exemplified by the rabbit technique, where a comb of harmonic orders are used to photoionize a gas target And then by adding an auxiliary infrared field, we produce replicas of the initial electron wave packets, and at the same energy, they interfere in so-called sidebands. And the oscillations of these sidebands follow twice the laser frequency because we have two laser photons involved in this interferometer, let's say. Now, the phase of this oscillation contains a wealth of information on the interaction process. In particular, it contains information on the ionizing radiation phase, the harmonic phase, and that was a key for the development of Attosecond metrology back in the 2001 and 2003 with the discovery of the chirp of the Attosecond emission. Then later on, it was realized that we could also access the smaller atomic phase term here, which corresponds to the phase of the two-photon transition dipole matrix elements. And these are, of course, intrinsic to the gas target. Actually, this phase term can be decomposed in two. First, the single photon scattering phase, and a continuum term coming from the additional contribution from the laser field. So why is this scattering phase interesting? Well, back in the 50s, Wigner showed that the scattering phase is directly related to the delay of an electron wave packet scattered by the potential with respect to a freely propagating wave packet. And this delay is called the Wigner delay, is related to the spectral derivative of the scattering phase. Of course, these Wigner delays are a few tenths of attoseconds, so very small, and it's only Attosecond spectroscopy that has been able to access them. First in solids, then in molecules, and finally in atoms. Here are a few early references, but of course there are many more. I apologize for those that are not showing here. Okay, very well. Now the question is, can we access also more complex ionization dynamics, like the ones that we have close to strong structural features like resonances? This is a question because there we expect that we will have fast phase variations. And so the dynamics cannot anymore be described by a single group delay. And for instance, if we consider autoionization here of helium, we have a direct path to the continuum, or we can populate this doubly excited state that is coupled to the continuum through configuration interaction. And the interference between these two paths leads to this famous asymmetric Fano profile, and also to this fast varying scattering phase. So can we access this using quantum interferences? And the answer is yes. Now we use, again, this rabbit scheme where one of the harmonics is now exciting a broad electron wave packet around the resonance, and the other harmonic serve as a reference electron wave packet. And now the phase information on the resonance is encoded in the sideband. So a first way to extract this information is to scan the laser frequency. That means we scan the harmonic across the resonance here, and we record many rabbit traces. That was done in an early paper by the Lund group. The other possibility, what we did in Saclay, was to use a highly resolving electron spectrometer so that we can encode the whole phase information in a single rabbit spectrogram and actually improve the rabbit technique with spectrally resolved analysis of the sidebands, which we have called the rainbow rabbit technique. So from this, we can get the amplitude and phase variation across the resonance. And this is shown here. So in the amplitude, we recognize this Fano profile, and in the phase, the expected very fast phase evolution. Actually, you see an excellent agreement with the dashed lines that corresponds to simulation by the group of Fernando Martin and also the group of Richard Tailleb in Paris. So now we have access to both the amplitude and phase, spectral amplitude and phase of the electron wave packet, and we can use this information to reconstruct the wave packet in the time domain. Actually, we can use any spectrotemporal representation, and here we have chosen a time-limited Fourier transform that shows how the resonant electron wave packet builds up in the continuum. So let me play it again. Okay, so you see in the first instance, we have a quite symmetric spectral profile, which corresponds to the direct transition to the continuum. And then later on, when the resonance starts to leak into the continuum, we see appearing destructive or constructive interferences to build up finally the Fano profile of the resonance. So this is one way of representing the electron wave packet. There are other types of spectrotemporal representations, like the Wigner distribution, and that was proposed by David Busteau in the group of Anne Lhuillier, where we did these measurements. So the bottom line is that we are able indeed to access quite complicated ionization dynamics using quantum interferences. However, up to now, we have assumed that the electron wave packet can be described by a wave function. That means we can just characterize the spectral amplitude and phase, or the temporal amplitude and phase of the wave packet, and we have full information. However, there may be some additional sources of decoherence. And first, we can have decoherence in the ionizing radiation, for instance, due to pulse-to-pulse fluctuations in the temporal profile of the Attosecond pulse, or we can have spatio-temporal coupling at the focus in the target gas jet. And this always results in a statistical mixture of electron wave packets in our multi-shot measurement. Another source of decoherence, as we have heard yesterday in the talk by Robin Santra and just now by Mark Bracking, we can have entanglement between the emitted electrons and the ion. For instance, if we have multi-channel ionization. Finally, we can have also decoherence in the detection of the electrons if the spectral resolution of the spectrometer is not infinitely thin. Okay, so to deal with all these sources of decoherence, we cannot rely anymore on the wave function description. We have to build a density matrix. And the question is, how can we access this density matrix in attosecond type measurements? And what we will be seeing now is the technique named mixed frog for frequency resolved optical gating of mixed states that has been proposed by our colleague Charles Bourassin-Boucher from Institut d'Optique. He initially proposed this technique in the frame of decoherence in the ionizing radiation. And we recently generalized that to all the sources of decoherence, and also we applied it experimentally. This is a technique that is in fact a generalization of the frog-crab technique to mixed states. So we need to reconstruct the density matrix of the electron wave packet. We know that the diagonal elements of the density matrix simply correspond to the population of the different levels. So it is given simply by the electron spectrum. Now we need to access the off-diagonal terms that measure the coherence between these levels. And a first order coherence can be obtained simply with the rabbit technique, where we couple the two neighboring harmonic peaks or energy levels in sidebands and encode information on the relative coherence in these sidebands. Now you see that we are still missing an off-axis element that corresponds to a higher order coherence between the outermost energy levels. And to obtain that, we need to increase the laser intensity so that we have higher order sidebands that will couple the two outermost harmonics. And now we expect that we will have 4 omega oscillations in the trace that will encode the coherence corresponding to this off-axis element. Okay, now an equivalent representation of the density matrix can be obtained in the time domain by Fourier transforming along the two energy variables. And now the diagonal element corresponds to the average shape of the attosecond pulse train. And the off-diagonal terms actually correspond to the interference between individual pulses in the train. Okay, so now let's see how we can obtain that experimentally. So here are, we did the experiment in Saclay. We were generating harmonics in neon and filtering them with a double filter of aluminum and zirconium, so that we have only 4 harmonic orders from 39 to 45. And we photoionize neon in the outer shell. Okay, now you see here the spectra when we increase the laser intensity from a few 10 to 11, which is the standard for rabbit type measurements, so where we have only low order sidebands, to 610 to 12 watt per square centimeters, where we now have higher order sidebands, as you can see here, that will couple the outermost harmonic orders. And now we measure the full spectrogram by varying the delay from -100 to +100 femtoseconds. And here is a key point. We wanted to test whether in standard spectroscopic conditions, we have already decoherence sources. So we chose very standard conditions. So we ionize a single, let's say we have a single ionization channel. Second, the stabilization loop of the delay was off. And third, we use standard magnetic bottle time of flight electron spectrometer. And now we use the mixed Fourier algorithm to reconstruct the density matrix. So here is the result. So on the diagonal, as I said already, we have the spectrum of the electron wave packet. And off diagonal, we have information on the, okay, here are the rabbit type of coherence, which is measuring the coherence between neighboring peaks. Then we have the second order coherence here with 4 omega oscillations, if you will. And finally, 6 omega in here for the outermost higher order coherence. And you already observe that we have very low amplitude in these higher order coherences, so that if we now integrate the modulus square of the matrix elements, to get the overall purity of the system, we get only 0.11, which is far from the 1 value that you would expect if you have a fully coherent scenario. If we now try to understand why we have so low coherence, that was quite a surprise for us. We now move to the time domain. And now it's clear that we have missing coherence. As you see, well, okay, this is the, on axis, the average attosecond pulse train. But when you go off axis, as soon as you have t minus 2 prime larger than 10 femtosecond, you have missing elements. So this is decoherence on the femtosecond timescale, but we also have decoherence on the attosecond timescale. If we make a zoom of the grains here, we see that they are oval shape. That means that we lose coherence of axis. So what are the reasons for these decoherence? Well, in quantum optics, it is usual to develop models of the various potential sources of coherence, of decoherence, and then to fit these models to the experimentally measured density matrix to determine which are the actual reasons for this decoherence. So this is what we did, and the best fit that we could get was obtained for this model. You see here the reconstructed density matrix, which has really the same features, the same features as the experimental one. And so now we can interpret the loss of coherence on the femtosecond timescale by the limited spectrometer response. And actually, if you think about it, it's quite easy to understand that when you want to measure the coherence between times that are far apart, like 10 femtosecond apart, you need to be able to resolve spectrally very narrow features. And of course, these features are smeared out by the spectrometer resolution. So that's the reason for the femtosecond decoherence. And for the attosecond decoherence, the reason is simply due to the arrival time fluctuations of the XUV pulse, or so to say, the instability of the delay line. As I showed you before, we lose the higher order coherences that measure the coherence between the outermost harmonics. Okay, very well. Now we have characterized all these, let's say, technical sources of decoherence on our beamline, and then we can use it to investigate decoherence sources in the photoemission process itself. And this is what I'm going to show you. Okay, so just before, the nice thing about these models that we can recover the fully coherent attosecond pulse train, which corresponds to a 26 femtosecond pulse envelope, let's say, with pulses of only 370 attoseconds. Okay, so now if we want to try to probe multi-channel ionization, for instance, I'm going to present a few recent simulations in a very standard case. Up to now, we have been looking only at the ionization of the 2p shell. But actually, if we look at low energy, low electron energy, we have additional channels coming into play, ionization from the inner valence 2s state, and also shake-up states that correspond to electrons from the 2p that on their way out shake up or excite another electrons in the 3p state. And actually this situation of overlapping channels was investigated theoretically by Feist and experimentally by Isinger in the group of Henrivier. And what we wanted to test was whether the mixed frog technique would be able to see a difference between fully coherent scenario where the two channels are fully coherent, or when they are fully incoherent. Obviously, in this case, they are incoherent. And we wanted to see whether the mixed frog could identify the number and the value of the different channels. So we consider these two extreme scenarios, full coherence and full decoherence, and we simulate the corresponding spectrograms. And you can already observe differences between the two. In the incoherent case, when you add the infrared, you of course have this oscillating sidebands, and you have loss of coherence or loss of contrast because of overlapping incoherent dephased oscillations. While in the coherent scenario, you have distortions of the oscillations. Now we can reconstruct the corresponding density matrices. In the incoherent scenario, not surprisingly, we have intra-channel coherence. So if you look at high energy, which corresponds only to the 2s channel, you have all the off-axis diagonal coherences. And in the low energy corresponding to the shake-up, you also have the off-axis of diagonal coherence point, but you miss clearly the inter-channel coherence that you, of course, have in the fully coherent scenario where you have a purity of 1. Now, if we try to apply the spectral theorem, that means we decompose into eigenstates, we can get for the incoherent channel two orthogonal eigenstates with significant eigenvalues. And you can already observe immediately here that these are exactly the two channels associated to shake-up and 2s. So without any knowledge included in the analysis here, the algorithm is by itself able to find these two ionization channels. And then when we Fourier transform, we get the ionization dynamics. And we have, for instance, a very small attosecond delays between the two orthogonal, let's say, attosecond pulse trains due to the different attosecond delays of the two channels. Now, for the coherent case, of course, we have a single coherent eigenstate. And now the temporal profile is very much distorted due to the beatings between all these energy channels. Let me, before jumping to the conclusion, acknowledge the contributions of my colleagues in Saclay for this second part, in particular Lou Barrow, Christian Alexandridi, Margherita Cioccolini, Dominique Platzer, Thierry Ruchon and Fabien Carré, and of course, a lot of thanks to Charles Bourassin-Boucher at Institut d'Optique for developing and doing this excellent job in developing this mixed frog technique. So the conclusion, the rainbow rabbit was applied and shown to be able to recover complex ionization dynamics, and then the mixed frog can be used to reconstruct the density matrix and so identify the sources of decoherence. So I will stop here. Thank you very much for your attention.
Thank you very much, Pascal. Now we have time for questions. I already see questions in the chat area, Q&A area, and I'd like to answer to pose this question from Tobias Witting. In the mixed frog rabbit scan you presented in the first part of your talk, the time delay was not stabilized. You used this as an example of decoherence. Have you checked how the retrieved decoherence changes when the interferometer is stabilized?
Yeah, not yet. Not yet. Actually, we stopped the experiment when we moved to our new lab, Attolab. This experiment was done, was the last experiment performed on the old Pelfa laser that was in Saclay. And then we had a 1.5 year interruption because of the building of the new lab in Orme-des-Merisiers, Attolab. I hope you had the opportunity to visit it. In any case, you are all welcome to visit that. And so now we are again in position to test this and hopefully see how much we improve this this coherence. But the main point is that with these decoherence scenarios or these decoherence models, we can really remove these decoherence sources and access to very fine details that would be otherwise invisible if you do not apply this mixed frog technique. So obviously this will be even more easy to do once we have stabilized the thing, but this is not mandatory, I would say.
Okay, thank you. I have another question from Robin Santra. Robin, do you want to ask this question in person? I think your mic is
Yes, I can. No problem. I will. Yes, so I think this is extremely interesting work. And my question is, the density matrix that you're showing is a function of E and E prime. So it's very strictly speaking not the actual density matrix of the photoelectron, because the photoelectron really has more degrees of freedom than just energy. So you would in principle require density matrix as a function of K and K prime, and in principle also spin. Now, what are the prospects of actually determining the full reduced density matrix of the photoelectron?
Mm-hmm. Yeah, thank you very much, Robin, for the interesting question. Yeah, actually, this density matrix corresponds to what we can get using our experimental conditions. So, as I mentioned, we were measuring the electrons with magnetic bottle electron time of flight, which means that we are integrating over all emission angles. So, of course, this information is lost. Now, if we image the electron momenta, for instance, using VMI, velocity map imaging spectrometer, then we will have access to this emission angle. Of course, this adds a further dimension in our measurement, and this start to make a big matrix of data. But definitely, yes, this is what we are heading to now. The objective would really be to measure with VMI the full mixed frog trace, and to try to include now in the density matrix the K vectors. Now, the other dimension that you mentioned, the spin, that will be then another story, because we have to, in neon, the spin orbit splitting is extremely small. So we don't have the resolution, I think, to get access to it. We can have it in argon and krypton. So probably we will be able to do that in the future.
Thanks.
I have the next question from the audience. Marcel Levenstein, and I'd like to also ask to switch on the microphone if possible. Otherwise, I will read. Yes, thank you.
Okay, and I think I was just commenting that maybe if you have access to this density matrix now, you can try to apply all these things that we were discussing in the previous talk, entanglement witnesses, or even bell tests, because you have much more information in a sense. I don't know how interesting it is, but of course it is much more difficult to determine the presence of entanglement for the mixed states than for pure states. But maybe you can do it because you have tomography. It's just a comment. I'm not attacking you, my dear friend.
Thank you, Maciek, for the comment.
Thank you. And one more question from the audience, from Tobias Witting. Tobias, do you want to ask your question in person?
Can I talk? Yeah.
Yes.
I guess you kind of answered this in the answer to the previous question. So my question was about the angular integration in the magnetic bottle spectrometer. So how does that influence the mixed state retrieval algorithm? Because in for crop, we know that we should not integrate over angles.
Yeah, that was a question that we had also, whether we would see some decoherence due to the fact that the phase gate that is applied by the dressing field is not the same depending on the electron emission direction. Of course, the electron emission is confined along the polarization direction. And we think that this is a reason, and this has been tested already there have been a number of papers showing that there was very little influence actually of this electron emission integration in the Fock-Krab trace. It was not inducing big enough distortions in the full spectrogram to prevent reconstruction with a Fock-Krab. And in our case, we do not identify significant decoherence due to this. Thank you for the question.
Thank you. Thank you, Pascal. Thank you, everyone, for this session. I'd like also to thank the speaker for the excellent talk and for handling questions very well. And I'd like to move on to our next speaker, Katerina Forzi. With that, we'll continue on the quantum interference in imaging. So, Katerina, it's your presentation now.
Let me share the presentation. Here it is. So good morning. And well, first of all, thanks to Carla and Andrew for inviting me to this very nice workshop, online workshop. Okay, so today I will try to contribute by discussing quantum interferences in atomic iodoral harmonic spectroscopy. Let me have the pointer here. Okay. So, well, this is an outline of what I'm going to talk about. I will give a very short introduction to iodoral harmonic spectroscopy. I think probably all of you are familiar with this, but I will just revise a few concepts. Then I will show you, well, the system we were interested in studying, which is xenon, and in particular the giant resonance xenon, and some results that we got by applying two-color iodoral harmonic spectroscopy in this system with our experimental results and the interpretation, or at least the struggle we are having in interpreting these results. So let's start with a very introductive three-step model for the iodoral harmonics. As you all know about the process, we have the external laser field that can detach an electron from the valence shell of the atom by tunnel ionization in the first step. Then we have the propagation of the free electron, which is accelerated by the laser field, and then we may have the recombination and the energy, the kinetic energy of the electron is released through the emission of an XUV photon. And this can beautifully be let's say, depicted in a quantum model, which is the Levenshtein model, that relies on two main approximations, which is the strong field approximation and the single active electron. So we basically ionize only from the outermost valence shell because of the tunnel ionization probability. And then we can write our harmonic spectrum as an integral of this expression, in which we can really recognize the ionization step, the recombination step, and the propagation, which is associated with these phase gained during the propagation by the electron. And I mean, for the dipole matrix element, one can use the hydrogen-like atomic dipoles, as here. And so then next step could be to basically relate these integral to electron trajectories in a simple way with saddle point approximation. What one can do is basically consider all the points which are basically ionization time, recombination time, and photon energy that are coupled, in which this phase, the derivative of this phase is zero. And so like we can write the spectrum as a sum of trajectories. And well, this is very nice because it's really related to the very simple three-step model. And it can give insight in the in a lot of experiments done in order harmonic spectroscopy. Basically, what happened is that like you can do an attosecond experiment just by collecting your harmonic spectrum. And this is because there is a natural mapping between the electron recollision energy. So this is an harmonic spectrum. And each harmonic, each electron recollision energy corresponds to a specific trajectory, and so a specific ionization time and recombination time. And so this mapping is basically like, so you have the attosecond nature of the process that is mapped in the harmonic spectrum. And so how does this is affected by quantum interference in higher order harmonics? Well, basically what happens is that in ionization, you may have different paths that are initiated during the ionization step. And then you can have recombination with a system that has many electrons that are maybe rearranging, and this electron can scatter with the recombining electron can scatter with the electron in the ion. So somehow like you can have interference also in the recombination step. And the point with harmonic spectroscopy is that all these possible phenomena are inside the harmonic spectrum. So it's a kind of an easy way to collect the information experimentally, because you just have to collect the spectral intensity. But then like you need a way to disentangle this information from the spectrum. And how this can be done? Well, a relatively easy way is to manipulate the electron trajectories. This is our clock. So the time between ionization and recombination corresponds to a trajectory and to a specific photon energy. And like you can achieve basically the control of the electron trajectories. This allows you to control basically the pump-probe delay in your experiment. And how can you do that? Basically by tailoring the external electric field, which is driving the electron in the propagation process. This can be done in different ways. But one way, which has been, quite effective, is to add a second color to your fundamental driving field. Here is a sketch of how this driving field looks like. You have the second color, and then you can change basically the delay between these two components, so the phase between the two colors. And what happens is that the second color displaces the electron away from the parent ion, and it can basically make the electron recombine or not, depending on the kick that the second harmonic is giving to the electron and the change in the electron trajectory. So this is a small movie in which you can see trajectories in this two-color field. For the electron, the blue dot is the parent ion, and then like when you see a colored trajectory, this leads to recombination, and it's a different color because it's a different photon energy emitted for each of these trajectories, corresponding to a different phase delay of the second color component. So basically what happens is that you have the second color that acts as a gate that selects a specific trajectory with a given energy. And there is an optimal phase delay between the two colors that maximizes the probability of recombination for each of the photon energy, of the harmonic photon energy. So this phase as a function of the photon energy is a measure of the time between the ionization and recombination time, and it's your clock to probe the dynamics. Here you can see a calculated experiment in which you see like this is the photon energy of the harmonic spectra, and here you have basically the phase that optimize each photon energy. Here you can see basically that it goes like this. This is SSP calculation, and here you have like that. Basically, your phase increases up to the cutoff, and then it goes down beyond the cutoff. Okay, and so well in the lab, this is a relatively easy experiment, and what we have done is that we used a driving laser, which is an OPA at 1.5 micron with 20 femtosecond pulse duration and 1 millijoule energy, and we did a simple setup for basically adding a second color with perpendicular polarization. And well, we retimed the two color in order to be overlapped in time, and then we have a pair of few silica wedges that can change the phase easily of the two color. And then we generate harmonics as usually by focusing this two color laser field on the gas jet with a pulse bulb, and then we acquire the harmonics with a flat field spectrometer. And yeah, well, basically we were helped in setting this up, and we established a very fruitful and long collaboration for doing two-color harmonic spectroscopy in our lab with the group of Neri Tudovic, and in particular also with Ada Seufer and Barry Brunner. And they, well, we did several experiments together, but this is one of them, basically. So these techniques, it's a promising approach that has been established many years ago by Neri, I think still when she was in Canada. And here I just show three examples. One is very recent of the application of this technique in order to study, for example, ionization and recombination times, or different pathways initiated during the ionization. And then you have, like, for example, here, these interferences that you can see, and you can see structure and spectral phases in the experiment. So this is just like some state of the art. So what we did, it was that we decided to study xenon. In the next slide, I will explain you how we developed this idea. But basically, like, xenon is, it's very nice to work with in the lab because it has a very high harmonic yield. It can be modeled quite easily, or at least this was what we thought before doing the interpretation of this experiment. And it shows electronic coloration because, of course, it's a big atom. And in particular, what happened is that there is this phenomenon known as giant resonance around 100 eV. And well, it works like that. Like, you can have ionization from the 5p orbital of the xenon. And then when you have the recombination step for generating the harmonics, you basically have two channels. You have a first channel in which the returning electron recombines directly with the 5p electron vacancy. That is this part here. And then you have a second channel in which the returning electron promotes an electron from the 4d inner shell to the 5b valence shell, and then the recombining electron recombines with the 4d electron vacancy. And so these two interfere constructively and give rise to this giant resonance, which is very well known also in photoionization at the synchrotron with photons of 100 eV energy. And well, what happened, it was that we, in end of 2013, we read this paper from Stefan Pabst and Robin Santra, in which they were reproducing, like, basically what they were doing, it was to model the harmonic spectrum in xenon and looking at the role of the giant resonance, so of the inelastic scattering happening in the recombination process. And what they found out is that they could switch on and off the different channel, and so switching on and off the multi-electron effects. And they were able to identify the contribution of this scattering in the final spectrum. So we contacted Stefan, and we said, okay, this would be nice if we can try to use two-color iodine harmonic spectroscopy to measure this recombination time, so this time of the electron scattering during the recombination. So we performed the experiment. This is an experimental result from 2014 that Davide Facciala performed in our lab. So basically what you see here is that this is the harmonic spectrum. This is the photon energy. This is a sequence of harmonic spectrum acquired for different phases between the two color. You can see like the periodicity here. And then we started, let's say, the interpretation of these results. Like, we can look at one of the period here, and you can see the behavior. Well, basically what you can do is that you can retrieve the experimental phase that maximize each photon energy with Fourier analysis, and you get the black curve here. It's quite noisy where you don't have a lot of photons, but I mean, like, you can see the behavior, the black line behavior here, which is quite clear. And then the first thing that Davide did was to calculate basically the theoretical phase that you would expect with strong field approximation, single active electron, and saddle point. And the point is that basically, and this is the blue curve, this blue curve is overlapped to the black curve only if you have a cutoff at 71 eV. So this was the first thing that was struggling us back in 2014, that we were somehow able to see trajectories beyond the cutoff. We have a huge signal beyond the cutoff. And it took us a long time to believe this signal and give an interpretation to this. But in the end, basically, like now we trust, also because of different experiments, that we have this cutoff at 71 eV. There is a clear change of the slope of the phase at this energy value. And so we can see trajectories beyond the cutoff. And this was already a nice result. But then we have a discrepancy between the black and the blue curve, which, I mean, we thought, okay, this may be due to the fact that the blue curve is single active electron. We are dealing with the multi-electron effect. So maybe that this discrepancy is hiding the information about the recombination time and the scattering time we are looking for. And so what we tried to do at first was to kind of adapt the strong field approximation, the single active electron strong field approximation, in order to, let's say, take into account multi-electron effect. And how can we do that? Well, we basically adapt the perturbative approach proposed by Dror Shafir and the group of Neri Tudovic in 2012, that does not consider the phase associated to the propagation along the perpendicular direction, along the second harmonic field direction. And then we also use a complex dipole calculated with a random phase approximation instead of the hydrogen-like dipoles for the saddle point calculation. So we change our saddle point equations to this one. And then what happened is that around the resonance, you get new recombination time that differ by only 20 attoseconds with respect to the original one. So we thought, okay, this is actually the right timing for this recombination process that we would expect. So maybe we are really sensitive to this very tiny delay introduced by the multi-electron process. But unfortunately, this was really an unlikely coincidence. Okay, first, I show you here. So this is our experimental result again. Here you have the black curve, which is the experimental one. Here you have basically the single electron saddle point, as I showed you before in blue. So here I changed the color, it's in red, unfortunately. And then I have these, the new curve, the new phase, considering the new saddle point obtained with this model that we try to correct with the random phase approximation phase. And you get the blue curve. And this is, I mean, like it's really overlapped to the experimental results. So this was why we were saying, okay, so like we succeed in getting some information about the timing of this recombination process. But then we discussed with Misha Ivanov. He pointed us out with our mistake, because I mean, we cannot really, it's not, I mean, our measurement is not perturbative. We have to solve the problem in 2 dimensions, and we have to consider the phase due to the second color component. And if we do so, what we see is that we basically get a new adapted multi-electron saddle point phase that is corrected with the random phase approximation, but I mean, like with the dipole from the random phase approximation, but then it's completely overlapped to the single electron. So it's basically with this approach, we don't go really farther. So this technique, it's not sensitive to this small change in the recombination time. We cannot see it. It took some time for us to convince ourselves of this. And probably it was kind of, I mean, like one can actually expect it, because I mean, the solution must be a saddle point, right? And if you have a very small change of the recombination and ionization time around the saddle, this doesn't really modify the complex phase, and so it cannot really modify the harmonic intensity that much. And this can basically interpret physically in the way that the second harmonic field has no enough time to displace the electron and change the recombination probability. So we are left with our discrepancy. And so it's not a modification of a single trajectory. there may be other trajectory contributing. Maybe this is some kind of interference of different paths that we are looking to. And then we said, okay, now we need to have a contribution from some ab initio theories that may shed light on our measurement. But the configuration is quite challenging from the theoretical point of view, because like we broke the cylindrical symmetry, so there's like the three-dimensional problem, because we have the second color in perpendicular polarization. And then xenon is a huge atom, we discovered that, so with a lot of electrons that, and you need to include the inner states if you want to look at the role of the 4D orbital. And we discussed with people about these, like we had also a discussion with Armin Strinzi about the possibility for doing that, but at some point, luckily, Stefan Paz pointed us to Andrew Brown for the Queen's University Belfast, that was able to perform the calculation of our experiment with the R matrix with time dependence. So basically, for me, this is a kind of a black box, but it's solving the semi-relativistic time-dependent Schrodinger equation for general multi-electron atoms and molecules in intense, ultra-short, and arbitrarily polarized laser pulses. I guess this could be, it's probably the title of this paper. And well, so we asked Andrew to perform the calculation in our experimental condition, which is also challenging because we are dealing with mid-IR pulses, long wavelengths, so long excursion time of the electron. And he did perform calculation in three conditions. So including only the 5p orbital, including the 5p and 5s orbital, and including the 5p, 5s, and 4d orbitals. And now I will show you the results that he got. So with only the 5p orbital, you can see here, this is an harmonic spectrum. And with the experimental parameter that we gave him for performing the calculation for a certain phase, then you can get the cutoff is 71 eV as in the experiment. And then if you do the two color scan, this is 4 phases basically here, and the white line is the phase that maximize each photon energy. You can see a behavior which is similar, let's say, to the one that we expect in the single active electron picture. So it rises up to the cutoff and then it changes the shape changes beyond the cutoff, basically. And we don't have signal here above 85 eV because we have exponential decree of the harmonic signal, and then we have computational noise rising up. So it's like it's only up to 85 eV. Then if we add the 5s, this was really good news for us because something was changing and we were starting to understand something. We see basically a secondary cutoff appearing if we add the 5s orbital. And this is basically could be compatible with direct tunnel ionization from the 5s orbital that we didn't expect at all in our experiment. But I mean, like apparently this is really compatible with our results. And the two scalar can, so this is the spectrum and you have the two cutoffs, and then you can see the two color scan, and then here you can see a change of the slope beyond the cutoff, which is something that we also see in the experiment. So this was already quite really a good news for us because something was, let's say, we start understanding. It's more complex, which I mean, but it start to somehow sort out. Then we add the 4D. And what happened is that basically in this way, you basically enable the inelastic scattering and the giant resonance. And in this way, what you have is that you have an increase of the signal around 80, 90, 100 dB. And basically you can see here from the harmonic spectrum, so the full orbital calculation is the yellow one, and you have basically an increase of the signal in this region here, which is associated to the giant resonance. And here you can also see some structures which also are mapped in the phase. Like here you can see the phase delay, still 4 points. And here you can see like that beyond the cutoff in this region here, you have several interference patterns appearing basically. So like the giant resonance acts to a boost to make us able to clearly see the signal beyond the cutoff, but also there are these interference that appear. And well, these results are relatively recent, and we worked quite for a long time as well to, let's say, to be able to perform this calculation and to, well, and to compare, like to get in the same experimental, in the same condition as our experiment. And well, now we are in the process that we have these results and we need to compare with our experimental results. So I don't have yet a real conclusion, in the sense that it appears that we have two basically ionization channels. So we may have ionization from the 5s. But this means that then we have like basically different family of trajectories we deal with in the recombination. And then we have the inelastic scattering taking place for the recombining electron, both from the one ionized from the 5p and the one ionized from the 5s. And these are affected differently by the giant resonance, by the inelastic scattering. So now, like if you look at the black curve here, which is our phase, the experimental phase, and the white curve here, there is still like something missing. It's like they are not similar. We understood up to some extent, and we are now trying to figure out exactly how much information can be extracted from the comparison of these two results. So in conclusion, basically, I showed you a study of the xenon giant resonance that started back in 2014. And we hope that after 6 years, we will be able to actually give an interpretation of these results. For sure, like the giant resonance enables seeing features that are not possible to see otherwise. And this is such trajectories beyond the cutoff. The harmonic spectroscopy beyond the cutoff is very sensitive to quantum interference. So this could be like a way to do spectroscopy in this region to see tiny quantum interference structure. We failed to adapt the single active electron strong field approximation for grabbing the information about the recombination process. But RMT unveil the process, unveil for sure the photoionization process to an extent that we were not expecting before. And probably we will also be able to grab then some information about the recombination. And because of course, like we may be then sensitive to interference between multiple recombination channels in this condition. I would like to acknowledge, well, this is my group in Milano, and I would like to acknowledge Davide Facciala, because he did all the experimental work and all the strong field approximation calculation for this very long project. And then finally, if I have a minute, I think so, I would like to make an advertisement, since I hope there will be students in the audience. Recently, with also Mark Bracking is involved, we started a Marie Curie innovative training network called SmartX, the study of carrier transporting materials by time resolved spectroscopy with ultra-short soft X-ray light. You can see here that we have 15 PhD positions available in a big consortium with many people working both in experiment theory and in industry. And so, I mean, if anybody is interested to apply to these, I mean, just get in contact, because it will be a nice opportunity starting in the autumn. And with this, I thank you for your attention.
Thank you, Katrina, for the excellent talk and amazing results. Now we have time for questions, and I can see that already Manfred Dine is the first to ask. Manfred, do you want to use your microphone?
Yes, can you hear me?
Yes.
Yeah, thanks, Katerina, for the nice talk. Very interesting. I would like to know, I think you did not say anything about the selection of short and long trajectories.
Yes.
I guess you did select them somehow in the experiment. Did you also select them on purpose in the calculation, or was it just using the overall spectrum?
Okay, so well, I mean, in the experiment, we suppose that we select the short trajectory as usual by the position of the gas jet. Then you can see here this noise here. I mean, like when you go to the cutoff, then there is not clear separation between the two. So we may have interference between the two trajectories, but beyond the cutoff, you should have only one trajectory. In the calculation, I mean, we did the selection in the strong field approximation, while in the, I think I'm not sure about what to say on the RMT calculation, which
I can jump in, Katerina, if you want. Sorry, to talk about the RMT calculation. We didn't do any selection. When we tried to do the selection, we introduced a lot of spurious numerical noise. So we just stuck with the overall spectrum for the RMT calculation.
Thank you, Andrew. I wasn't sure. I remember discussing this point, but not sure about the outcome.
Okay, thank you. I think that was my main question. Thank you.
Thank you. And I have another question from the audience. Manfred, sorry, Zdenek Masin, do you want to ask your question in person?
Hello, can you hear me?
Yes.
Okay, I just want to ask about the possibility that your signal is the result of interference of some other pathways. So actually, it's very well known that the xenon giant resonance actually has two components, which are very wide and overlapping in energy. So have you considered the possibility that your signal is the result of interference of these two recombination pathways?
Yes, I mean, it's like, I think there is also a paper from Stefan pointing out this.
Exactly, yeah.
So we did consider it. The point is that before having Andrew's simulation, basically we got convinced that we were not able to look at the recombination. So we didn't expect to have interference in the recombination step with our technique without having another ionization channel. Now we will, because I mean, like what you can see from the experimental data is that you have two slope changes. And at the very beginning we thought, okay, then these two slope changes are associated to the two different processes. It will be very nice. That was my, let's say, hope at the very beginning. That was few years after 2014, but still few years since now. But then like turned out, okay, like in the development, we cannot really see that. Now we got back to the possibility that we are seeing something because we have basically the time to affect the trajectories due to the different ionization channel. And so then we will get back to consider this possibility. That should be, I mean, included in this also, Andrew, you can jump in if it's wrong, but I think it should be considered in the full calculation, including all for the shell. So yeah, that would be cool.
Thank you. Thank you.
Thank you, Katrina. Now I think we can move on. I'd like to thank Katrina again for your exciting talk and being so expressive and emotional about the results. It's important when we see this. Important for the online presentation. So thank you very much.
Thank you.
And now it's time to move on to Klaus Bartschat on the coherent control and attosecond dynamics with pulse, XUV, and infrared radiation. Klaus, can you now take over the share screen?
Yes, good morning, everybody. Can you hear me okay?
Yes.
Okay, good. Well, let me start by thanking the organizers to invite me to speak here and apologize in advance in case I sound a bit incoherent. It has to do with the fact that it's still pitch dark in Des Moines, Iowa. I should also thank the NSF for supporting our projects in various ways, and many contributors to these talks, experimentalists as well as theorists. On the left there, the ones in blue are either studying or working at Drake University. The ones in green do not. And then there are some who are sort of in a coherent superposition between working with us or at us and somewhere else. So this will be a pretty fast overview of recent work in our group. in the spirit of this meeting, a couple of attoseconds per slide. So, but I will have lots of links also to papers, to video talks that we uploaded to YouTube. And also, if you are interested, I'm very happy to share my slides with you. So there's a couple of topics, starting with an introduction. And we don't really have to do much about this. Everybody here knows that. The difference between multi-photon ionization and tunneling ionization. I'm going to talk about both of those. The Keldysh parameter is the one that determines what happens. One other thing I'm going to talk about is the so-called frustrated ionization, and that really is sort of a strong field process, except that the field may drive the electron back, and it could get stuck in a bound state. So computational methods. Two things. One is very popular, single active electron approximation, SAE. There you have sort of a nice situation. You have a potential here for helium R times V. Then you have a bound state orbital here, and you might have a continuum orbital. So this is, they are very fancy, very fast methods to solve this problem. It's very economically, if you need to average over the carrier envelope phase or the focal point, etc. Right? Then the other one, we just heard about it from Katerina, the RMT method, which is a multi-electron method, is very computationally expensive. Catherine Hamilton, who is now my postdoc, and so she studied under Andrew Bown in Belfast, and she has a nice little YouTube talk about the B-spline, the R matrix method, as well as a project that she's doing with me, namely to combine it with Oleg Zatsarini's B-spline R matrix method. We also have a very good collaboration with the group of Alexei Gromzhemaila at Moscow State University, and they use time-dependent perturbation theory to obtain various parameters, and that can help quite a bit as well. So first topic, light-induced coherent quantum control. This is with linearly polarized light. We all know that if you have two pathways that lead to the same final state, but you don't really know which way you're going, you can get interference. And the first topic I want to talk about is something that we did a few years ago, where you take the fundamental and the second harmonic of a femtosecond XUV pulse from a free electron laser, and you try to control the photoelectron angular distribution. So here is the scheme, and then I'm illustrating it on hydrogen. So you have two laser pulses, really, and you have a mixture of the second harmonic, which can get you right away into the continuum. So here, for example, I show this for atomic hydrogen. So if you start with the ground state, the second harmonic can get you right away over here. If you do it with the fundamental, you would need two photons. You can enhance the process by going via a resonance state, in this case, the 2p orbital. And as Mark, for example, also mentioned in the very first talk here, the result of this is that your angular distribution becomes sort of, there's a left, right, or up, down, depending on how your laser is oriented, a symmetry about this. So what happens is, essentially, because of this, your photoelectron angular distribution takes, this general form, but in contrast to what we are sort of used to from standard photoionization experiments, is that there will now be odd rank anisotropy parameters, these betas here, beta 1, beta 3, and so on, and they lead to an asymmetry that you can measure if you look, say, for example, what goes to 0 degrees, what goes to 180 degrees, difference divided by the sum, and that is an asymmetry, and you can actually control this via the delay. So this was the experimental setup at Fermi in the group of Kevin Prince. It was published a few years ago in Nature Photonics, and it was quite an amazing experiment. Of course, unfortunately, they don't do hydrogen, but they use neon. My friend Tim Gay at Nebraska calls neon the devil's atom, and because it's quite hard for theorists although RMT might be able to help out. And then they use these guys as the intermediate states. There are two of these J=1 states. But sure enough, as a function of the relative phase of the delay that they could control to 3.1 attoseconds, I just read the paper again last night, and they're talking about 900 zeptosecond steps in their delays. And so you see a beautiful sinusoidal curve as a function of this relative phase. Unfortunately, the blue line is a fit and not the theory, but at least theory predicts that this should happen. We then wrote 2 follow-up papers, and we looked at the dependence of all this, what you could see as a function of the laser parameters. You get beautiful pictures when you look, for example, you scan the photon energy through, you might change the ratio of the second harmonic via the fundamental, you can change the number of pulses, and as I said, you get beautiful pictures, but at the end of the day, it is very, very difficult to compare directly between experiment and theory for a system like this, although, as I just said, RMT might come to the rescue ultimately. I will also talk a little bit about, or quite a bit about, I should say, the overlapping of an XUV and IR fields. We wrote a paper on that, and so the question was, can we do something like this, but then on top of it add an infrared pulse, so another IT mixture. I don't have time to go into this, but in this paper we showed that the answer to this question, can we get additional control, is in fact yes. And so of course what happens, and again we learned about that already in various talks just this morning, you get sidebands, and if you have a strong IR you get more than one, and if you have a weak IR you might just get one. And that's what I'm going to talk next, speaking about sidebands. This is an interesting paper. This is basically Anna Hart's idea, and the idea is to compare single sideband standard rabbit. We spell rabbit with 2 T's because we think the 2 also deserves the T. And then with a center sidebands or other sidebands of a 3 sideband rabbit scheme. And the idea is to directly extract information about the continuum phase. So the details are in that paper, but here is the scheme. So this is sort of a standard rabbit. You would make an APT, attosecond pulse train, say with 400 nanometers in this case, and probe it, and you would get what we just heard about, standard interference, but you can also do it with 800 nanometers. So in fact, here you make the APT, in fact, with the second harmonics. And then you have a lot of pathways, but you end up here, you'll see that there is a possibility again that there will be interference because you've got lots of pathways, and in fact in the middle you get something that looks very much like what you are used from the rabbit experiment. I should say that it's also that these lines also oscillate, but it's hard to see on this particular scale. So one can already see that this thing here might be very helpful, and the idea is to look at this and at this in 2 different experiments, take the difference. It's a very, very challenging experiment. There's no doubt about it, but the idea seems very nice. So let me just show you how this thing would look like. This is a computer experiment. We did it for atomic hydrogen. That's what we know how to do very well. So you would get these high harmonics. I didn't label them all just not to confuse the picture. And then you have the sidebands, the center sidebands. They are the weakest ones. They have the best contrast, but the other ones also exist. So you have lower sidebands and higher sidebands in between all of these high harmonics. So as I said, they oscillate. In this case now, because this is 400 nanometers, it's 4 times this, omega p times tau. But you see, the thing is, what happens is there's 2 delays really. One is the delay between the IR and the XUV. So this is this TD here. And then there's another one that one could write as delta phi, or in the spirit of attoseconds, one would like to get tau in here. And so what you see on this picture is the center sideband, the oscillation of the center sideband. And you see that this extra phase here, the difference to zero, that kind of, it goes like a line like this. So the higher ones will have less of a delay than the lower ones. So here it's about 80 attoseconds. This is about 30 attoseconds. And 1 IR period in this meeting is 2,668 attoseconds. As I said, the other sidebands also oscillate. Here is one example of a lower sideband. The contrast is, you can see, is not very good. But it is possible to fit. Divya Bharti, who is a PhD student of Anna's, did these fits. And so if you fit the highest energy sidebands, you get something like this. And you see here that this delay is just a few attoseconds. And you basically get the same information from the lower, the center, or the higher sideband, which is important to check a particular approximation. If you go for the lower sidebands and you look really carefully, you will see that these sidebands do not exactly have the same time information. There's a little bit, this is a bit more here, believe me, than this. So it turns out to be somewhere between -70 and -85 attosecond. Unfortunately, you can also see that the fit is not quite as good as it was in the previous one. So this is where you have to, as an experimentalist, you have to take the balance about, do you want a good fit, you want signal, and all these little things that theorists don't have to worry so much about. So here is basically the results. So a typical example, and we make, we look at this extra phase. So part of it comes from the APT, part comes from the Wigner delay. If these are the same in the 1 sideband and 3 sideband rabbit, then the difference, so this is a real challenge, right? The difference can give you access to this continuum phase directly. Then one can make an approximation to that, which is very complicated in general, but the approximation is you just add them up for the various transitions. And there was a formula given by Markus Dahlström and collaborators, which was then used in this particular paper. And it turns out it's actually a very good approximation, at least for the high sidebands. For the lower ones, it's not so much. And you see actually a difference here between what you would get from the higher and the lower sidebands. As I said, it's a very challenging experiment, but it certainly can be done. We also looked at what might be happening in a realistic experiment. You might have chirp. And so again, the question is there a difference between the phases that you get from the various sidebands? And it turns out that this is very small. So that's good that the chirp, these are numbers that Anna gave me, and she said they are kind of realistic. So the chirp actually doesn't do much. There's a little bit that the IR chirp does, but at the end of the day, this difference stays the same. So that's good, but there's absolutely no doubt that this will be a very, very challenging experiment. So if we have a student who wants a challenge, sign up with Anna. Also, please look at Anna's and Catherine Hamilton's Twitter posters on this particular topic. And in fact, the same Twitter poster and Catherine's day2-am talk, which is now on YouTube, should be looked at, because the experiment is actually planned on argon with 10,030 nanometers rather than 800 nanometers. But Catherine did a heroic RMT calculation. And so what you see here, in fact, is the difference that you would get if you do the best fit between a 400 nanometer and an 800 nanometer probe for argon and neon. And you can see what is required to actually measure that. But we are assured by the experimentalists that they are going for it. Well, very impressive. Another thing I would like to mention is an experiment that was also done at Heidelberg. And this is the idea. Again, you have an XUV and you have an IR. You can delay. Here are the two examples of extreme cases. One is when the IR is late. The other one when the two pulses are overlapping. And this is well known that in principle, then when you have an overlap, you can have these light-induced states where you do something that you would normally do with the XUV, but then you absorb one or two or emit one or two IR photons, and you get that. Aaron Bondi, who is a visitor at Drake, gave a nice talk about that at DayMob as well. So what can circularly polarized light do for you? So this is an experiment that was done also at Fermi by Markus Ilchen, Michael Meyer and collaborators. And so they had a rather strong XUV pulse that can ionize helium, but the wavelength was tuned so that it could also at the same time excite the ion to the 3p state with m equals +1 in this particular case. And then you can play with the helicity of an infrared pulse, and you need 4, or depending on the strength 5, to get into the continuum. And the question is, what would you see if you change these helicities around? And so here's a simple scheme of this. What you might see, the full lines here are sort of lowest order perturbation theory. The dashed lines are higher order processes. And so what happens? Now let's see. This is what happens. You get a peak. This is the lowest energy peak, the rather low photon electron energy. You get an ATI peak. There is some kind of presumably noise in between. And so the question is again, so how does experiment and theory compare? So this one is helium plus ultimately, so we should do better than that in general than for neon, for example. And indeed, I think we are doing pretty well, although one has to say that we cheated a little bit on the pulses were too long. There was not quite, the intensities were a little bit shaky, we didn't know, but overall it looks pretty good. And so the next thing then is to look at the angular distributions, and this is basically what you would expect from first order perturbation theory, and it works quite well, right? So if you take co-rotating, you only have one spheric harmonic, really that does the job. In the other case, you may end up with essentially predominantly coherent superposition of those two. These are the dominant contribution. Then we looked at the circular dichorism just of the main line, and there was a bit of a surprise. At relatively low IR intensities, like about 7 × 10⁻11 watt per centimeter squared, we got what we expected from lowest order perturbation theory, namely that the co-rotating case dominates completely. So when you define the circular dichorism in this way, the probability for the same ionization with the same helicities compared to the difference over the sum, then you get this. Then what happens here is you just double the intensities and you already get almost 0. And that was a big surprise. At very high IR intensities, there is a prediction it should be negative, but we were very surprised at this particular energy. So what's going on? In this paper, we tried to explain what's going on. Alexei Gromzhemaila really did a lot of work. It has to do with the quasi-energy spectra. What happens when you have this NIR as a function of intensity? And what happens basically is that we are losing the target for the co-rotating case. And that is the main reason for this particular circular dichorism to go down. I also wanted to talk about circular dichorism in lithium. This is the same idea, basically, except now you don't need a free electron laser, so you can almost do it at home. This is done at Rolla in Daniel Fischer's group. The theory was done in our group. David Atrishala is a very good undergraduate student. So we just submitted a preprint to the archive. So the idea is to prepare lithium in a trap with circularly polarized light, and then you ionize that oriented state with circular polarized light, compare also to the 2s ionization, and you see what the difference might be. So the interesting thing is that there is actually, what happened here? Okay, there it is. There is actually a possible application, because you might be able to make electron pulses where you can switch the polarization within femtoseconds. and that could be used to study ultra-fast spin dynamics in magnetic domains. Here is sort of one of our results, experiment compared to theory. And so you see the agreement isn't perfect, but it's pretty good. And we again get a circular dichorism depending on what the intensity, the peak intensity of the lasers are. And so there is some broadening, as we can see, but overall it looks pretty good. David gave a talk about it. You can listen to it on YouTube. Last topic that I'm going to talk about is tunneling and frustrated ionization. Well, thanks again to all the people who helped me out, especially yesterday already on this. Most people will know this paper that became quite famous in Nature Physics. And so what they did is they introduced this Atto clock idea. And at the end of the day, the point is that if you measure this angle, then supposedly you might be able to figure out whether or not there's a time delay in photoionization. The problem is that the Coulomb interaction plays a role, and that's a little bit of a disturbing fact, because that already causes an angle. And sure enough, if you take a Yukawa potential, Jan Michael talked about that yesterday, you essentially sort of get a zero angle, but the reality is that you have several of these cycles, and so you get some of these bands, and that is a problem. Nevertheless, the experiment was published. There's good agreement between the experimental data and the theory. One might say, well, that gives confidence in both. As arrogant theorists, we would say, well, we solved the TDSE for atomic hydrogen. We know how to do that. So it's good for the experimentalists that they got this. The hope originally was that these results could be used to calibrate the Atto clock for future studies on more complex systems. Whether or not that is really possible is a subject for debate, as we had yesterday, because it turns out that it's not quite so simple to determine this particular angle. And so we found that it depends on how what your algorithm is to get this angle. You might have a cutoff experimental momentum, whether you take the maximum, whether you integrate to some extent also on the pulse parameters. And so I don't believe that you can predict this angle with a simple model. For a Yukawa potential, indeed, it is basically zero, independent of those parameters. In the previous graphs, the same procedure was done and everything is fine. I would like to point out that Alex Bray made exactly the same point. If you took the first fringe here, you would get this angle. If you take the last fringe, you would take that angle. Some of you may know that the Brays and the Barchards are good friends. I've known Alex since he was 4 months old. He's not my son, but I was ready to say, that's my boy. That's exactly what I wanted to hear. So we try to explain it with Bohmian mechanics as well. I don't have time to go into the details, but if you are interested in, please read this paper. We then proposed to use negative ions, because Yukawa really is wrong for neutral targets on both sides. You need to change the Z near the nucleus to get it, and then at large R, you also have it wrong. So we had this. We can put the basic physics in it. It was interesting. It took us a while to get this published and accepted, because people said, well, there's no way on earth you can do the experiment, but that's not quite correct. In fact, Dag Hanstorp in Gothenburg in Sweden just wrote a proposal to actually do it. And we can even put a bit more physics in. We heard from Lars Madsen yesterday about dipole polarizabilities and so on. So this is our SAE result. It's very, it gives essentially zero. Then there was a recent follow-up by our RMT friends, and they actually found a negative offset angle, but please read that paper in detail. So I want to very briefly at the end talk about frustrated tunnel ionization with linearly polarized light. And so we just published a paper on this. Then we looked at the ellipticity dependence. There is a preprint on the archive right now. The paper has practically been accepted. The idea was to test RMT against SAE. It works very well for this particular parameter. There's also a function, a simple analytic function by Alexander Lanzmann And that also seems to work. It's a little bit too narrow. There's a prediction from a Chinese group that says if you increase the length of the pulse, it goes up even to non-zero ellipticities. Not quite true when we checked it. And I should also point out that this, in fact, is not the measured signal that we calculate, but we believe that the signal is essentially proportional. And I should say these are all relative parameters, so it's a little bit, one has to be careful about these conclusions. So summary, there are many systems that you can study. Much is done with SAE. Direct comparison of this experiment remains a challenge. Numerical calculations beyond SAE, most likely RMT, are coming. They're very demanding, and the interpretation is by no means obvious. And I should say that our group, we believe, is well positioned to perform a variety of calculations. We love to work with experimental colleagues, and so if you're interested, please talk to us, and I thank you for your attention.
Thank you very much, Klaus, for your exciting talk. Very clearly explained, was really enjoyable to watch. And now we have time for questions. I see already the first question from Luke Roundtree. And Luke, do you want to ask your question yourself?
Sure. Can you hear me?
Yes.
Yeah.
Sure. On your slide about the three sideband RMT, or three sideband rabbit calculation, sorry, you made an approximation for the continuum time delay. Is there any physical justification for that approximation?
Well, that is a very good question. It's sort of an asymptotic. It's a fairly complicated situation. If you read the Dahlström et al. Paper, there may be other people in the audience who can answer the question better than I can. I don't know if Anne is there. She might be the best one to answer this, but I don't want to put her on the spot. It sounds like a good possibility, and it works well. You know what? I don't really know enough about this to really.
No problem. Thank you very much.
Thank you. I have a question from the audience. From Andrew B from QUB is asking, can you explain how the negative ion experiment will be done?
Can I explain it?
Can you explain? Yeah.
Well, yes, in principle, I could, if I could quickly look at the proposal that Doug sent me and asked for help. I have to say, I don't know. They will buy the correct lasers for it. And apparently he's very confident that they can do this. The negative, ion affinity is 3.5 electron volts for these systems roughly. So the idea is to use a long wavelength laser. I'm not an experimentalist, so I honestly don't know how they do these experiments. I have a brief 8-month career as an experimentalist, and I left the lab permanently in 1981. So, and that was on something completely different. So I honestly have no idea how they do the experiment, but I'm amazed at what they can do. So the best person to contact is Doug Hanstorp. He wrote a proposal to the Swedish National Science Foundation.
Thank you. I actually have a question. Can you, if you would have a chance to speak now to experimentalists, what would you ask them? What experiment would you like to see?
Well, the biggest problem that we seem to have is not in what experiment would you like to see. I mean, we would like to see, if we want to be bright as theorists, we want to see experiments on atomic hydrogen. Well, that's pretty hopeless, right? Very, very difficult. I wouldn't say hopeless. I mean, the people at Griffiths did it. The next thing is relatively simple targets. But on the other hand, progress is often made by doing something really challenging. So we have to agree on somehow to work, to move towards each other. Again, my field was electron scattering originally, and this is what happened. People came together, you know, they said, well, we can calculate this, we can measure that. It didn't agree. But then slowly but surely people overlapped. And so what I would like to see, to be honest, in many of these experiments is a better characterization of the laser pulses. So we are basically told, you know, we sort of have, we guess the peak intensities, and we think we sort of have a Gaussian, but we don't really know, and it's not pretty reproducible. And we have a focal point, and you should average over it, and you average over it like this. But we don't really know whether that is the correct way, because they don't know enough about this. So I think what I would really like to see from experiments is a better characterization of these laser pulses, so that it's not a matter of us having too much freedom, as, to be honest, we had in this experiment with the dichroism on the helium plus. There were basically, we twisted some parameters around so that it kind of looked good at the end, right? Now, in principle, we would say we as theorists should be able to do this, right? Now, there were additional issues were that the pulse was quite long. Nicolas Duguay gave a beautiful talk at DayMOP that you should listen to, and he made a lot of progress on this. But that's really the point that I'd like to see, is that the experimentalists know a little bit more about their actual experiment.
Thank you very much. Very good answer. And with this, I'd like to finish this session that was very enjoyable. Thank you very much, all the speakers. I'd like to involve all the attendees in some way. It's difficult through this environment, but at least can I ask everyone to raise their hands if you like the session, please, now? Thank you. And I run the applause again. We would like to give an opportunity to everyone to ask more questions, to chat with the speakers. So now we will put a link to the Zoom, to the coffee room Zoom, where you can go. It's going to be a different link, and talk to the speaker. So I'd like also to ask speakers to do the same, to go to the coffee room, and we'll see how that will go. And now you will see the link. So please do this now, because we are going to finish the session, and I suspect that this link will disappear. And with this, I'd like to thank you and finish the session. Thank you.